So this concludes for the repeated iterations. Let's see now the functions, how to write functions. Well, it's very flexible, Julia, because we can write function in very different way. The normal way is to use the keyword function, the name of the function, the parameters, and the body of the function. So this define functions. And here we call the function with the parameter 2, and we obtain, well, 2 plus 2. A function can be also defined in line without the function keyword by setting the equal operator here, and it's exactly the same things. Functions in Julia can be also be anonymous, that are with this arrow passing the parameter of the function to the body of the functions, and you can assign anonymous function to identifiers. As we said, functions are object and are first class object. They can be passed as a parameter in another function. We'll see later that do block, or they can be assigned to variables. Normally you don't do this one, in the sense that if you're using anonymous function, it's because you don't need to keep track to this function outside the context where they are used. But if you want, you can call you can assign to identifiers, and then you can, as the function name here, you can call this identifier to run the function. Function can be nested, as in this example. This is particular of Julia, so you can have one function defined another functions, and can also be recursive in the sense that the function can call itself. You have to put attention to have some conditions that returns, otherwise you may find yourself in an infinite loop. And also consider this is for the classical example of the Fibonacci numbers generator, but this is a naive implementation. There are much better and faster implementation, but don't use this recursive nature. Distinction between going to the function arguments. Distinction between the arguments is given if these are defined and for their position in the set of the arguments, or for their name. So in this function here, I'm using the two types. A is a positional argument, as well as B, while C is defined as a keyword argument. How do you know it? Because here I'm using the semicolon. So every parameter that is after the semicolon is a keyword argument. Every parameter that is before the semicolon is a positional argument. So in particular, here I have also a default value that make B an optional parameter. So when I call f, the f is the name of the function with just 2, what I'm doing here is that I'm using the default parameter 1 and 1 for B and C, and I'm calling with parameter A equal to 2. So you can see the result is 112 because B and C are 1, and I have A equal to 2. But I can also choose to call the function with the other positional argument or the keyword argument. So the keyword argument, when I call, I specify the name of the parameter, and here 3. One other thing is to use the split operator to have a variable number of arguments. So with the precision that when I use a variable number of arguments, the name of the parameter defining the variables variable parameter. Sorry, the name of the parameter name that define a variable set of parameters must be the last one within the positional arguments. So here it is fine. I'm taking the length and the sum of the arguments, and here I'm calling with 3 parameters, but I could put it for, sorry, what I'm doing, for 5, and the number of parameter of positional parameter here, I can do that because I'm using here the splat operator. So a few rules for positional and keyword arguments. Keyword arguments follow a semicolon, as I already said, and a positional argument without a default cannot follow a positional argument with a default provided. So here is fine because the default is the last one. I couldn't rewrite this function with a equal 1 and b. And the split operator to define variable number must also be the last positional argument. And what I didn't say is that when I call the function, I must respect this difference between positional argument on one side and keyword arguments on the other side. Some other languages, and in particular Python, allow to mix the two way of calling, while here in Julia, if I have a keyword argument, I define it here as a keyword argument. The only way I can do it is to call it, when I call it, is to use the name of the argument, and the same for positional arguments. For example, this one will not work. Another important fundamental aspect of the parameters for the functions is the types that is associated, and the fact that these different types allow to use the multiple, to call the same function with different implementations, so to call different implementations of the same function. And what is characteristic is that it is relatively simply to understand the usage of this multiple dispatch. What is complicated is to understand the very deep implications that this has for the program. So here I'm taking this example. I'm using another name to not mix up with the others code before. So here I'm defining a function free that take 2 parameters. The first one is an integer, and the second one is I'm saying that is a string. And to say that a parameter is of a certain type, I've used this colon here. I'm using 2 times the column to separate the variable name with the type that I want for it. So here I define the function, and here I call, well, with 1 integer and 1 string. Here I do the same, but I put the first parameter is a string and the second one an integer, and here I call it. And if I call methods for free, I will have 2 methods, one defined with integer string, and the second one with string and integer. So what is interesting here is that this full string and integer was dispatched to the correct version of the function, to the correct method that I defined here. And what is interesting really is that having multiple dispatch, we allow to compile a version of the function that is specialized for the argument that we are calling it. And this specialized version, it is compiled, but it's compiled at runtime when the first time that the function is called with that given parameters, and we will see again when dealing with type inheritance in the next segment. But one important thing is that unless we want to use this multiple dispatch to define a new method specialized for our type, we do not need to write the name here in the parameters. We just allow them. We just allow the function with the parameter without the type, and the type of the parameters will be inferred automatically by Julia. So normally doesn't have influence on the performance to add a notation about the types. And two important tips for improving performance. The first one is that the function will be compiled and will be efficient if it can be type stable. So if it is written in a way that given a specific set of types of the parameters, so not the value, but when you with the function receive a certain combination of types of the object that they receive has a certain combination of types, like here an integer and a string, the results must always be of a given type. It doesn't need to be the same, it can be whatever, but the type of the output depend only by the types of the input. If this is true, the type inference across the chain of function calls, so you have one function that call another function that call another function and so on, it can continue because it can guess the program continuously. Julia can guess the type of the of the input given when she know the output, the type of the output. If this is not true, this break the type inference and the performance become much worse. The second element to consider for performance is try not to use global variables unless they are constant in the function, but try to write the function in a way that whatever the function has to do is fully determined by the information that the function has in terms of its parameters. So it doesn't need to refer to global variables. The function we saw here, they all have one specific type, but can we write a function in a way that is even more generic? That is it that we write it once and then what it do, the function depends on the type. And here is possible, and it's possible by using templates, where you can see here I'm not writing the type of A. I'm only saying that is T, and this T must be a type that is a number. So these things I did here, this function I did here, really doesn't work only with integer. Why I have an integer? I can use a float, or I can work with complex numbers if parse works with complex numbers. So it works with whatever is a number. So why to write? I don't need to write this one for integer, for floats, for whatever. Let's put it in a more generic way. So with this syntax, I'm using a template functions. I define it here, and then notice here that when I call it with the beauty of this template, when I call it with a integer, I'm having the integer version of the function. When I call it with a float, so if I, just to make you sure, if I put it 1.5 here, it will give me an error because it will look for an integer. It's calling this function and will have replaced it because he understands that the argument is an integer, so he replaces automatically this t with an integer, but then he go here and try to parse this 1.5 as an integer, and he say no, I cannot do it, I cannot. So, but if I call the same function here with 1.5, automatically Julia understands that this 1.5 is a float, and he try to parse b as a float, and I have the correct results. So there are two different ways to do syntactically. Here we write where, and we define the type, the template outside where I define the parameters. Well, here I put the where clause within the parameters, and the difference is that in this case I can use this t within the body of the function. Here instead, in this case, I cannot use it within, so it doesn't give me an error. But if I call it here, I will have an error because it will say that he cannot find t. While it does that, because what I just said, but when you use this syntax here, then you can use t within the body of the function. While when you use this syntax here, you cannot have the body of the function. You cannot use t in the body of the function. One last important aspect about functions is the difference when you call a function by reference or by value. So this is the two typical way for different programming languages use a different syntax for one or for the other. When you call a function with the value of the argument is completely copied, and the function works on a copy of this value. While instead you call by reference, you are making in C is called a pointer. You work on reference to the same object. So whatever you do within the function is reflected and has an influence on the variable that has been used to call the function. Now, the way implemented by Julia is a sort of mix between these two, that is derived to what we said when we discussed type and objects. Depend on the characteristics of the object, if it is mutable or not mutable. That it is, if the object is not mutable, it is immutable. We can have the argument rebind to other objects. It doesn't make any effect to our original caller object, because the arguments are just new local variables that bind the same object. So here I have foo x equal to 10. This is immutable. This x here is my local. I could have called it the y just to makes it doesn't matter. This is a local variable, and this local variable here, no, sorry, I'm calling x because I want to see that it's the same. Well, no, really, it doesn't really matter. I can get it x or y, whatever. But this function does change the argument and make it equal to 1. So when I call it with my x here, I still have x equal to 10. It didn't become 1 because this is just a local variable that is x or it's y, it doesn't really matter. This local variable just rebind to another object, and when it rebind, it loses the reference to the original object that was here 10. So whatever happens to this variable doesn't have influence for the variable that is used for calling. Another very different way, if x is a mutable object, because if it's a mutable object, if I am rebinding the variables to something else, it doesn't influence our original variables, because it's just a rebinding to another variable and we lose the reference to our original object. But if I do modify, as I do here, I'm modifying my object, so x is equal to 1, 2, and I call this function, x change, because you can see here that has been modified, is the same object that is modified. If I call here another function here, foo 2x equal x equal 10, 20. So here you say, okay, I have what I do, it already has a value. I use it for other things. Okay, and x is my lock is equal to 1, 2, and then call foo 3x. What do you think here? Now x will be 1, 2 or 10, 20? It will be 1, 2, because this operation is not a modification like here, but it is a new rebind of this local variable to a completely different object. So at this point, the reference that it had to our original object, even if this object is mutable, is lost, and doesn't influence to the original variables. And attention that you will see often variables ending with exclamation point. This is just a name as another one, and by convention say that the variables defined with a name ending in exclamation mark do modify, put attention, do modify one of the argument, and normally it is the first one. So I should write here, instead of foo x, I should write, to be compliant with this convention, the name with a foo and a question mark. As last point of the segment, sometimes you have functions that take other functions as object. We saw that this is possible in Julia. And when this happens, you can use, instead of defining the inner level function and then call the outer level function with the inner function as a parameter, if the inner function argument is the first one, you can rewrite in using this do block syntax by calling the functions and defining the inner function at the same times. And here is an example. So here is a true function that I use in a machine learning library. Is a pull functions that is used to pull the neural networks and making pulling layers that reduce the dimension of the nodes, and apply a function. By default is a mean, but I moved his here, so here it doesn't have a default, and is apply this function to the pool size. So here is the definition, and I can take the mean, for example. I can define it with a mean. So here my inner function is a mean, and I'm taking the mean every 3, so the mean is 2, the mean is 3, this mean is 4, and the mean is 5, or I can write it with the maximum. So the maximum of 1, 2, 3 is 3, the maximum of 2, 3, 4 is 4, and so on. The same, because the first argument is a function, I can, as I said, call the function and define the inner function. Here I'm making another average, all in one go, employing with this syntax do. And in the syntax, in this do block, I specify the name of the local variables that I will use within the do, that are the parameters of my function. They doesn't need to have the same name, but it's important that they have the same number of variables. And then I apply this code here as the inner function to pass to the outer function that here is pull. And we'll see that do blocks are frequently used when we do input-output operations, in particular on files.